Do you ever get the feeling you're not alone? That's in the universe, or maybe even in our own solar system. Our speaker is a quantum astrochemist at the Center for Astrophysics for Harvard and Smithsonian. She investigates how molecules interact with light so that they can be detected on faraway worlds. She spends most of her time studying molecules that life can produce so that one day she can detect an alien biosphere. Her favorite molecular biosphere signature is phosphate, a terrifying gas associated with mostly unpleasant life. When she's not deciphering exoplanet atmospheres, she works hard to persuade the next generation of scientists to become an active part of the astronomical community. She will be busy when the Webb telescope gets fully up and running, which might be this summer. Who knows? She'll tell us more about that. She has other stuff going on too. She holds a doctoral degree in quantum chemistry from the University College of London and a master's degree in physics and astronomy from the University of Edinburgh in Scotland. Prior to joining the Center for Astrophysics, she served as a research scientist at MIT. Although our programs team kidnapped her from the TV show Nova, her work and commentary have been featured elsewhere on PBS, BBC, Wired, and the New York Times, among others. I sent you all a link to her fantastic TED Talk over the week, and it's also on our online calendar, our award-winning online calendar. Just check it out after this. So let's have an extra galactic welcome for Clara Sousa-Silva.
Hi all. I actually do all my work within the galactic neighborhood, so I do leave the extragalactic stuff for other astronomers, but thank you, I appreciate it very much. Should I share my screen? Are you ready for that?
Yes, you should be able to share your screen.
Okay. Now I have an optional music element to the talk, so I'll try to make that work, but if it doesn't, I'll share a link to it. Okay, I'm going to presume all is well.
Yes,
please interrupt me if it's not.
We can see your
good.
screen.
Excellent. Okay, so thank you so much for the lovely introduction, and thank you all for being here so early this morning for you. As Buddy told you, my goal is indeed to one day identify life beyond Earth. And today I want to tell you very briefly how I'm trying to get there by studying all the potential signs of life, even the really, really weird ones, and by training the next generation to join the cause. So how does the search for alien life happen? To answer that, I usually like to reverse the problem. So could an alien civilization know we have an inhabited planet? Imagine that alien astronomer was on the other side of the galaxy looking for a habitable planet in their night sky, and they pointed their telescopes in our general direction. We're about 2/3 off from the center of the galaxy. If this alien astronomer pointed their powerful telescopes at our sun, but not more powerful than the ones we're about to have with the Webb telescope that launched a couple of weeks ago, they would be able to split the sun's light into the sun's rainbow or the sun's spectrum. And this is exactly what they would see. They would indeed see the rainbow of the sun, all the colors, the visible colors, but also the invisible colors in the infrared and the ultraviolet. And they would see that there are imperfections, that there are bits missing of this solar spectrum. And that's because some of the light from the sun will have been absorbed by atoms and even molecules that can survive in the cooler regions of the sun. And they would leave behind these tiny shadows, which we call absorption lines. And that happens because molecules behave in a really unique way. So molecules still have to follow the laws of physics, like everyone else in the universe. But it's not quite the same physics as we are used to. And that's because molecules are so small that their physics follow the rules of the quantum world. And one of those very strict rules is that they can only absorb quantized amounts of energy. And these correspond to specific wavelengths of light. And these correspond to specific colors of a rainbow like the sun's. Now, different stars have different atoms and molecules, and so consequently, a different spectrum. And this one is just our sun's. So this alien astronomer could look at exactly where you're looking at now and use their universal knowledge of molecules that they got from their quantum astrochemists like me. And they would do this and know exactly what molecules and atoms were causing these absorption lines and use it to figure out the composition of the sun. But if they were patient and they were also fortuitously aligned, they would be able to notice that every 12 years, a few additional lines would appear and then disappear, and every 12 years appear again. And these lines would be due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. Now, an alien civilization with only marginally better technology than we have now, but very similar to what we'll be able to do with Webb, would be able to study these lines and know that Jupiter has a huge, complex atmosphere with not just hydrogen and helium, though those are the main components, but also methane and ammonia and hydrogen sulfide and many, many other gases. And if they were really careful, they might be able to see that every year, a few much fainter lines would appear and then disappear, and then a year later appear again. And these, of course, will be due to the molecules in our own Earth's atmosphere, also absorbing new lines of the sun spectrum. So those alien astronomers could just use this technique to try and get spectra for all of the solar system bodies. For example, here on the screen, you are looking at from the top, Venus, Mars, Jupiter, and the moon seen here from the surface of the Earth. And you can tell that even from this comparatively short distance on astronomical scales, they're really next door, the light from these very different planets can appear really similar to the naked eye. But again, by splitting up their light, you can see how drastically different they really are. Now, rainbows and spectra, the way I showed it, are really pretty, but they're really hard to work with. So what we do instead is that we use these lines, these spectral lines you see on the screen now, which describe light intensity changing at different wavelengths or colors. And these spectra are exactly how we interpret planets and their atmospheres. And these alien astrophysicists could indeed split the light of the solar system planets and tell the difference between them by looking at their different spectrum. And if they did that, they would learn that Venus is mostly hell with really high levels of sulfuric acid. So any life there will struggle, though I'll talk more about that later. And they will learn that Mars has a teensy tiny atmosphere that can barely shield its surface from radiation. So also not the most hospitable destination. And they would learn that out of the solar system planets, there is something really special about the Earth. And that is, we have a lot of life. You can think of our atmosphere and its subsequent spectra as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute an awful lot. Those alien astronomers would be able to know that on Earth, we don't just have an atmosphere, we have a biosphere, and we can do the same to them. Now, first, we do have to find the planets themselves, and we've been working on that for a really long time. We found Uranus in 1781, Neptune in 1846, Pluto in 1930, and then we lost it again in 2006. We found our first exoplanet in the mid-90s and kept finding more and more. With Kepler, we found thousands of planets, and with a test mission, thousands more. And with upcoming missions, we will find tens of thousands more. So we're getting really good at actually finding the planets. We have only just begun finding atmospheres on these planets, and we still know very little about them. Future missions like the JWST will provide more data on more planets and their atmospheres. And this means we are on the cusp of being technologically able to detect the molecular signs of life for the first time in Earth's history. Now, each molecule that could be associated with life, which we call a biosignature, has a spectrum of its own. And they look roughly like these on the screen and describe exactly how each molecule interacts with light anywhere in the universe. Now, if we want to detect any of these molecules in an alien atmosphere, we do need to measure or calculate the spectra for each one of them. This is possible, but it is difficult, and it requires a lot of lab work, often in really dangerous conditions, and a lot of computational work, which is the bit that I do, that requires really large computers and many years of simulations. But if we do use these spectrum to detect these molecules, on their own, they wouldn't necessarily indicate life, because all of these molecules have what we call false positives for life, by which I mean non-biological sources that can also release these molecules into an atmosphere, things like photochemistry or volcanoes. And this is true for most of the molecules that life loves. They're produced by life, but also by non-biological sources. And this isn't some cruel astrobiological coincidence. This false positive problem happens because these molecules are great, but chemically speaking, they're easy to make. So life likes making them, but non-life also makes them accidentally, spontaneously. And what this means is detecting any of these biosignatures by themselves on an alien atmosphere would not necessarily indicate life. Now, there are two solutions to this false positive problem. One is carefully considering context. For example, oxygen on its own may not be a very good biosignature. If our sun had different levels of radiation, or if our oceans were evaporating from an intense greenhouse effect, or if we had more CO2 and less volcanic activity, or if the trace gases in our atmosphere was simply different, then large amounts of oxygen could accumulate in the Earth's atmosphere without any need for life. But in the exact context of our planet, our sun, and the other components of our atmosphere, oxygen is a wonderful, robust biosignature. And the same is true for most molecules that one would usually want to consider in the search for life, those produced by life on Earth in abundant quantities. These molecules are only good biosignatures if they can be attributed to life after an investigation of their false positive scenarios. And that requires not just understanding the stellar and planetary environment, but crucially, the detection of other, potentially much less abundant molecules that can provide context to their discovery. Now, how many molecules could form this context? My old group at MIT tried to come up exactly with this list of all the possible molecules that could be produced on a planet and contribute to the spectra of an alien atmosphere. But that list contains 16,367 molecules. So the first problem is that this list is long, but it is finite, which is a really important start. But the second problem is that we currently only have the tools to detect a tiny fraction of these molecules, less than 4% of them. This means that our ability to understand the chemical and atmospheric context of any biosignatures we detect isn't great. And this makes it really difficult to resolve the false positive scenarios for these biosignatures. But these are biosignatures of life as we know it. But life as we know it is only probably one island in the vast archipelago of possibilities for life. Our galaxy has a huge diversity of stars, and orbiting them are planets of every kind. Earth alone has given rise to billions of different species. So it isn't a big leap to think that life itself can arise in a large array of unexpected forms, and that life will have many strange biosignatures beyond those that we are used to considering. Which brings me to the other solution to the false positive problem. And that is, we can look for molecules that, although are less popular, are biosignatures with very low or no false positives, and so they need less context to signify life. An example here, a very edge case example, would be complex pollutants, signs of industry, though that is obviously a rare situation, and we're hoping our alien friends don't pollute as much as we have. In fact, my favorite of these strange biosignatures with no associations with industry or pollution that has very low false positives for life is the phosphine molecule. Now, when I first started working on phosphine about a decade ago, well, more than a decade ago now, it was really not considered a good biosignature. In fact, at the time, phosphine was only known for two things. One, as a marker for really violent storms on Jupiter and Saturn. We have for a long time detected phosphine in the very upper layers of these planets, but it is already a little surprising to find it there because we know the temperature and pressure of those areas of Jupiter and Saturn are far too low for the formation of phosphine to be favored. But what happens is phosphine, after being happily formed in the hellish depths of these planets where its production is favored, is then aggressively dragged to the top by strong, fast currents, surviving to much larger concentrations than we would have otherwise predicted on the top where we can observe it. But on rocky planets like the Earth, we don't have those extreme environments like the depths of Jupiter. So phosphine is very rarely made spontaneously or accidentally. Which brings me to the second thing phosphine was known for. On Earth, phosphine is really mostly notorious for just being a lethal and foul-smelling molecule. Phosphine interacts fatally with oxygen metabolism, and that makes it a really effective killer. For this reason, we often use phosphine as a pesticide, and sadly, for exactly the same reason, we have used it as a chemical warfare agent for over 100 years in the First World War, and sadly, most recently by ISIS. So phosphine is mostly awful and deadly, but what I found is that it has one very important characteristic. For life that doesn't rely on oxygen, phosphine is perfectly safe. I confirmed this by reviewing all reports of phosphine detections on Earth. And I found that it's produced in all manners of ecosystems that are low on oxygen. So places like sewage, marshlands, rice fields, lake sediments, the intestines of fish, the intestines of babies, and actually seemingly the guts of most animals. Basically, life that doesn't really need oxygen is very happy to produce phosphine. So I wanted to find out, could we detect signs of a phosphine-rich biosphere on an alien planet without oxygen? To explore this possibility, we simulated loads of hypothetical planetary systems with a phosphine-producing biosphere. And we found that near-future telescopes would find it reasonably easy to detect phosphine on planets with lots of hydrogen or CO2 in their atmospheres if they were planets orbiting small stars, though these are the most popular stars in the galaxy. And it would find it quite hard, but still possible to detect phosphine on the puffy atmospheres of hydrogen-rich planets orbiting a sun-like star like ours. Now, these type of planetary atmospheres are quite common. We don't expect oxygen-rich atmospheres to be the most common type of planet in the galaxy, but we still don't know because we have seen very few atmospheres. Nonetheless, this made phosphine quite promising as a biosignature. But what makes it really appealing is that it seems to have no significant false positives for life, as long as it's found on rocky temperate planets. So definitely not a sign of life on Jupiter. To figure this out, we first looked at standard chemical processes for making phosphine, but we found that in all cases, the formation of phosphine was completely chemically disfavored. So at that point, we looked at more extreme situations like lightning or volcanism and meteors. And we found that even in the atmosphere types, which should be the most favorable for phosphine production, those that are highly reduced, only a negligible fraction of phosphorus could turn into phosphine and never any amounts we would be able to detect. So at that point, we looked into increasingly more extreme and implausible scenarios, and still none delivered any substantial false positives for phosphine. This means that given our current understanding of potentially habitable planets, we now had this tweetable conclusion for our work that read, any detectable amounts of phosphine on a rocky planet can only be explained with life. Now, when I submitted this work for publication in 2018, I thought this was a cool conclusion, but it really wasn't controversial because it was just me describing a totally theoretical, hypothetical situation. I was imagining a distant planet, a tropical paradise with a complex biosphere without oxygen, producing tremendous amounts of phosphine that we might one day be able to observe. And some of you might know that phosphine turned out to be a little more exciting than I had initially envisaged, because a few months after I submitted this work, an astronomer in Wales, Cardiff, Jane Greaves, reached out to me asking for help with interpreting a telescope observation, seen here in white. And 18 months later, another signal from another telescope, shown here in orange, both that seem to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on the planet. Now, Jane knew this was strange, but needed a phosphine expert to know how strange. And that's how our collaboration began. This notion that phosphine, a molecule I had claimed to be a promising sign of life, might be present on Venus is, of course, very exciting. And the press thought so too. But before we jump on life as an explanation, I should point out there's still much about Venus we don't understand. So all we really know is that something strange is happening. And currently, there is plenty of controversy surrounding this ongoing discovery. But ultimately, we need to address the primary uncertainties of the discovery. And those are, is the signal definitely real? If it is it definitely phosphine? If it is, what or who is making it? And to try to answer these questions, we're trying to do more observations with more telescopes that can help us at least answer the first two questions. But as we learn more about Venus, we can make more and better simulations of the clouds that can help us make sense of exactly what we're seeing there. Importantly, we also need more spectra for the molecules in the Venusian atmosphere that can help us figure out false positives for any biosignatures we might confirm. But what I want to highlight at this point is how a virtually unknown and quite unusual and disgusting molecule became such an important piece of the puzzle in the search for life beyond Earth. And phosphine is just one molecule, Venus just one planet. Even if it turns out that indeed we have found phosphine on Venus, this will not be the last time we find a potential biosignature on a planet beyond ours. So the question is, will we be better prepared to interpret such a discovery next time? Well, that's what I spend most of my time working towards. But it's never going to be as simple as detecting a single interesting molecule on an alien planet. As much as I love phosphine as I do, and as much as I like the more traditional biosignatures like water and oxygen, I don't expect that the detection of life will come from a single molecule. As the Venus story shows, the detection of life will likely be uncertain. And that uncertainty can only be reduced if we're willing and able to both detect and understand more molecules, even if they're not pleasant or abundant. To find life, we have to be willing to consider the big picture, not just a few promising molecules, but all possible molecules that can together help us reduce the ambiguity in the detection of life. But there are billions of stars in our galaxy alone, and orbiting them, billions of planets. And on them, thousands of possible molecules that we will need to understand, which is more work than we astronomers can possibly study on our own. And I came to this realization a few years ago when I was writing my PhD. At the time, I was also the head of education for the Twinkle space mission, which is planned as a teeny UK satellite for the characterization of planets. At the time, I delivered all the education and outreach programs for the mission, but I was doing this while I was also training as a high school teacher in a London school, which was a terrible decision because it turns out teaching is way harder than astrophysics. But I tried, I really did. And while I was trying to teach as best as I could, I did notice that whenever my research was mentioned in my classroom, the students and I would get into these super interesting discussions about my work. And that made me think, what if my students could also help us understand these thousands of molecules and billions of planets and stars? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own students to do research with me and 3 junior scientists who agreed to help. And this is the first cohort of students, which we split into 3 groups, each dedicated to studying the spectra of a molecule crucial for understanding alien planets and their host stars. So I would like to introduce you to Team Titanium Oxide, Team Acetylene, and Team Methane. These amazing kids learned astrophysics and quantum chemistry and programming, scientific writing, and performed original research on these 3 molecules. And they went from being my high school students to my official scientific collaborators and co-authors on multiple scientific articles. These students you see here then became mentors for next year's students and those the year after and so on. I did hire someone to replace me when I left the UK to move to the US, so the program continues on without me. And since 2018, more than 100 school kids have become published authors of peer-reviewed scientific articles through the Orbits program. To continue this sort of work in the US, I became the director for the Harvard-MIT Science Research Mentoring Program. I actually have just stepped down as director to focus on my research, and also because I'm very heavily pregnant, but we still have a small team of incredibly dedicated scientists and educational experts running the program. The general principle of the program is that we recruit about 3 to 8 junior scientists as mentors, mostly postdocs and PhD students, and we help them adapt their current research projects to benefit from a collaboration with high schoolers. But then we hire, train, and pay a salary to 10 to 15 local high school students and assign them to mentors with whom they perform original research throughout the academic year. At the end of the program, we organize a scientific symposium for the students to present their research to the community, and I would be thrilled to invite you all to attend next year's. So we now do have a lot of young people working towards discovering the signs of life on alien planets. And that's great, because ultimately it won't be the next generation of telescopes that will revolutionize astrophysics, but the next generation of people. In the coming years, we should do all that we can to help them. But looking for life is very much an interdisciplinary science. We need astrophysicists, engineers, biochemists, and quantum chemists. But when the time comes, we will also need philosophers and poets if we're ever going to make sense of it all. So the last thing I want to show you is what happens when you add musicians to the list. This here is the phosphine spectrum, the true phosphine spectrum, which I did spend my entire PhD simulating. This deceptively simple spectrum is actually formed from the collective force of 16.8 billion tiny spectral features, all of which I've painstakingly calculated. And each of these billions of features represents a very particular form of quantum vibration of the phosphine molecule at very specific frequencies of light. The vibrations at particular intensities and frequencies is exactly what music is. So I recently collaborated with the composer David Ibbett, who was able to map the spectral behavior of phosphine to the audible range, effectively sonifying phosphine. So this is what phosphine looks like, but this is what phosphine sounds like, transformed into a solo cello piece that captures the complex quantum behavior of the phosphine molecule. Recently, I was lucky enough to hear Minjing Chung perform this piece, and I invite you to check out the sound of the terrifying and mysterious phosphine molecule, since we currently have a very unofficial rehearsal video on YouTube. For the sake of time, I'll post a link in the chat so you can all see it. So here are the takeaways from this talk. To be able to understand alien planets and ultimately to detect life, we'll definitely need bigger and better telescopes, and we're working on that. Within the next few decades, we'll be able to point these very expensive, bigger telescopes at a potentially inhabited planet, and we'll be able to look at these planets' atmospheres. But today, we aren't quite prepared to both detect and understand the presence of most molecules on an alien planet. So my biggest professional concern is not that we'll fail to detect a habitable planet in our lifetime. It's that we will point our expensive telescopes directly at an inhabited planet and just not have the tools to know it. By collaborating with people of all ages and fields, and by considering all possible molecules that could form the context of an atmosphere, I aim to provide the tools to understand alien planets so that one day we'll know life when we see it. Thank you.
Thank you so much, Clara. And by the way, T-shirts for Team for Phosphine are available outside for $15. So we love that. And we'll accept questions now. I'll begin with one. Pass them around. Here's one for you, Clara. We can now access quantum computation via the cloud. There are quantum computers sitting up there. Are you able to tap into that from time to time for your massive quantum computations?
So I know it seems tempting that quantum computers would be good for quantum simulations, and maybe one day, but currently they just don't have the accuracy we need. So we do have to use supercomputers, but we do have to, and it's many stages. So at the first stage of the calculations, we do need just very large, very big processors. And at the second stage of the calculation, we can parallelize these calculations. So we can use, just throw GPUs at it. So certainly very recent developments in computing have allowed us to make this work theoretical, and that has been a huge advancement and a recent one. But quantum computing is not quite there yet. Maybe one day, but as you can guess, the the priorities are not to figure out my obscure molecular spectra.
More interesting though, yes. Right. Rich?
Yes, Doctor, thank you very much. First of all, observation, and that is what you talked about, the kind of people that will be needed to move this forward. You did not include lawyers, and I think that was a wise exclusion. But I get a real fundamental question though, is to say we're looking for life. If you could, what is the definition of life that is being used? So what is it, I guess, that we're actually looking for?
Excellent question. I do think we need to include lawyers. I have some talks where I also mention lawyers. I do know, honestly. So I have some of my colleagues are specialists in space law and space ethics. And so this is very much, it's very much a thing to try to define, for example, as an extreme example here, one of the theories for how we can really capture the light from the sun, which a lot of people think it's an inevitability for any advanced species in the universe, is to try and not waste most of the solar light, is to build these giant structures that can capture light. And so to do that, we need materials. And so there's some talk that to build these giant structures, we obviously can't use the earth. We would have to dismantle the earth. And some of the ideas that we could just take mercury apart for parts, just, no one's using it sort of attitude. And as you can imagine, this is a pretty divisive proposal. And so this is where lawyers would come in and ethicists to try and define what we can do versus what we should do. But in answer to your other question, to which I have only a slightly more serious answer, is that life is still a controversial definition. We still don't know exactly how life originated on Earth, though we know it did in several forms. Astrobiologists do disagree on most things, but we do agree on a very basic definition of life, which is whatever it might be, it has to metabolize, or some version of metabolism. Meaning, in the universe, things aren't 100% efficient. And so any life, no matter how weird, will have to be in an environment, make use of that environment, do something with it, and then waste some of the product or produce some waste products. And so metabolism, the notion that you will release something back to the atmosphere as any life form, is one that is mostly agreed upon. So that's what I use. I just look for signs of metabolism, signs of some action being done in the local environment that then releases things. When I first moved into the house that I'm in right now, one of my neighbors within like a month when I was outside said, "Hey, I Googled you. Are you really an alien fart expert?" And I couldn't deny it. Because it's kind of true, not quite what, little Clara looking up in the skies was hoping to be famous for, but you can't really choose what people will know you for. So.
All right, next. Here we go.
Doctor, that was a fantastic talk. I think your work with students and frankly your work in investigating the outer reaches of the universe is just mind-boggling. My question, as a seriously ignorant layman, is you're looking for molecules that we know. Is there a possibility that there are elements out there? I mean, we just discovered the elements we know over the course of, I think, the 19th century and maybe a little bit later. What's the possibility that there are elements out there and therefore molecules that we can't even envision yet?
So we know that the laws of physics are universal. We're able to test them and see them in action. But we do know the laws of chemistry are also universal. We are still finding elements, but these are not stable elements or common elements. So although we might still find a few more, these are not elements that are popular throughout the universe. And we know this is true. We can test the average abundance of different elements of the periodic table around different places in our galaxy and beyond, and they seem to be quite stable. This is not surprising because we know how they form through supernovas exploding and neutron stars merging. And so we have been able to predict the abundance of these elements, and we've been correct. So we do know that the physical laws of the universe are universal. We know that chemistry is also universal. The laws of chemistry are universal. The question here is, though, are the laws of biology universal? And that we don't know. So we do put a lot of work into looking at different weirder combinations of the periodic table and try to figure out if different biochemistries, completely hypothetical biochemistries, would be able to achieve complexity playing only with what we know are universal laws of chemistry. And it's all very speculative work at this point, but we do find that if life makes certain biochemical choices, it will forever be limited in the complexity it can achieve. But some biochemical choices just require a different solvent, for example, less reliance on water like we do. And that is a really interesting avenue, though, as you can imagine, it becomes even more speculative at this point. So we do try to be agnostic in that we don't consider life on Earth to be the template, but we do consider the periodic table as a pretty solid starting point because throughout the universe, it seems to be exactly what we expect.
Wow. By the way, we have a question beamed in from my friend Peter on Zoom. What books are you excited about reading?
Well, I spend so much of my time thinking about aliens that I actually haven't read science fiction in a long time. And so when I read books now, I try to read books that have nothing to do with science. Recently, I became really into a book by Nicholas Barker that is all about the problems and complications of digitizing the historical newspapers of the United States. And it's a fascinating look into libraries and how we treat knowledge in their physical forms. And so I recommend that my students always have a wide breadth of interests. And so I try to not just talk that talk, but walk that walk.
Thank you very much, Doctor. I really enjoyed your presentation. Fascinating. Using the absorption method that you described, aren't you limited in your research to just those planets where we're on their same solar plane? And are you investing that at all?
So excellent question. That is true. For this technique to work, we literally need to be aligned between the star and the planet. And this is only a very small fraction of all the planets in the universe. But the first important thing is it shouldn't be a special fraction because there's no reason to think that we as people have a special perspective. And so whatever we find, we can multiply by all the other perspectives we can see and figure out the statistical significance of the things we find. But it's still quite distressing to think we're missing all of these potentially very cool planets. So we do have other techniques that don't use this passing in front of the star technique. It's called the transmission technique. And one of them is just direct imaging. Now, this is a much simpler one to understand. We find a star, we try to block the light from the star and allow us to see the very, very faint light that a planet will be producing. And we can do this. But as you can imagine, the contrast is so large that so far we can only do this for planets that are really big and really hot. And so this technology is a few decades behind the one I'm describing, but it has the major advantage of not being biased by our unique angle, our unique perspective in the galaxy. So we're trying it all, but these different observation techniques tend to be complementary rather than one is the solution to it all.
Yeah, there was recently a telescope that was launched, and I read that they unfolded the leads, or whatever you would call it. It's the largest, parabolic telescope, I guess, to date. Can you talk about that and the impact on what you're doing?
Yes, so this telescope is the James Webb Space Telescope, which we call JWST or just Webb. And it was launched on December 25th, just gone, Christmas Day. And it was delayed. At the original launch date was 2007. So we astronomers have been waiting for this moment for a really long time. But it had something like, I don't remember exactly, but something like 532 single failure points. So everyone was just sleeping poorly for many, many months in advance of the launch. It had to be carefully folded in this incredible feat of mechanical origami because the mirrors, the actual telescope itself is so large, it could never fit in a rocket. So it had to be folded and then slowly unfolded in space by itself. And because we needed quite far away from the sun and the earth and the moon so that the light and the heat from these planets doesn't contaminate its data, we will never be able to service it. So if anything went wrong in the launch or while getting to the orbit, that's it. And we're talking $9 billion spent on this telescope and the career of every astronomer I know, myself included. But it has finished unfolding as of this weekend on Saturday. It finished unfolding. So we've all been sleeping much, much better recently. And it is an incredible telescope. It has this diamond-shaped sun shield the size of a tennis court that shelters it from the heat of the sun and the earth and the moon. And these are 5 really thin layers of material. I mean, human hair thin layers of the sun shield protecting it so that it can be at an extremely hot temperature on the sun side, and that gives it power, it has solar panels, and an extremely cold temperature on the side facing away from the sun, where we have these beautiful mirrors. They're 18 hexagonal mirrors covered in gold. And gold is chosen because it is a very good material for reflecting infrared light and reflecting it into our instruments on the telescope. And the reason for that is because infrared light is a really underused series of wavelength in observatories because it is so hard to use infrared light without any heat from the telescope, which is infrared light, damaging the observations. And so if we didn't protect the telescope with all these sun shields, the only thing the telescope would see is itself because it's the hottest thing around. We're in, the vastness of space. And so this is an incredible telescope. It is indeed the most complex, powerful telescope ever put into space by a long way. And it will be looking at planets in our galactic neighborhood, and it will be able to look at their atmospheres in the infrared. And it just so happens that these molecules, these biosignatures that I love so much, they love absorbing in the infrared. Is a very popular place for quantum behavior. And so we will be able to use the Webb telescope to look at planets in our galactic neighborhood and look at their atmospheres and detect molecules. So this is a huge deal. And I'm very excited. And I have a lot of observations led by others that I'm on the team to indeed see what's going on. But I should emphasize that although Webb is a really near magical instrument, it won't quite have enough accuracy and resolution to see many molecules. So we won't be able to get that full context of an atmosphere, but we should be able to detect the main components of the atmosphere. And in some of those atmospheres, we may be able to detect if something is off, if there's a molecule that shouldn't be there because it's in chemical disequilibrium. And that already will be a very suspicious thing to see and a very good reason for them to build a telescope that can focus exactly on that planet. So a lot of hope is set on Webb. And I'm very excited that it's all the risky bits are done. It is now just almost at its home and it's fully unfolded. So now we're just testing all the instruments, but I couldn't quite believe how well it all went.
Thank you, Doctor, for a great talk. My question is sort of on the ultimate goal, that if you perhaps find life, or you think you find life on some planet somewhere, it's still probably billions of miles away. What can we send there to research or find more about it?
So you're right. Any life that I find will very, very likely, unless it's in the solar system, be way too far for us to ever reach them. But this isn't a bad thing. The likelihood that any life we find is compatible with our own is near zero. The most likely thing is that if we met, we would contaminate each other in horrible ways. In fact, several of the tests we've done with potential biochemistries that alien life could choose, we would literally melt each other on contact. We're just two piles of goo. So I don't think we should be aiming for, a close relationship with any alien life we find. I am of the opinion that modern astronomy should be more about looking and discovering things remotely. I would like the public and scientists too to become comfortable with the knowledge that we can obtain from far away, to shed the need to always go, to always conquer, to always have feet on the ground. And so I am hoping that people don't need to actually have the aliens come over or have us visit to feel the sense of companionship, to feel that we're not alone in the universe just by knowing they're there. So I am not a proponent of human missions beyond the solar system. I think we should explore this one and see the other ones from far away. But even if I was, it is an engineering feat that even hypothetically we haven't figured out.
Doctor, as a lawyer who knows nothing about space law, but I do raise the question in my mind from time to time, why in the world would we be, why in the atmosphere or the universe would we be the only planet that has life similar to ours? And so my question, I'm disappointed to learn that the life out there may be goo that would melt us. If you were to go to Las Vegas, what would be odds that you would post on whether or not we would find at some point in the billions of planets life similar to ours?
I would say those odds are very slim. I and many of my colleagues think life is inevitable. We haven't figured out if life is common, but there is no reason to think we, as a life-bearing planet, are special. There was nothing particularly special about the molecular cloud that formed our solar system. There's nothing special about the dust that formed the Earth. There's nothing special about our sun. There's actually some unusual structures in the position of the planets in our solar system, but it's by no means extremely rare. And so to think that after all this lovely mediocrity, Earth is suddenly very special as the only place in the universe life arises, seems to me like the height of hubris. So I certainly don't subscribe to that view. But given the diversity of the composition of atmospheres and planets and their relationship to their host stars, there's no reason to think that life out there would be anything like ours. Even on Earth, where there's just the same planet, the diversity is enormous. And in the early stages of life on Earth, the atmosphere had no oxygen. And so life was completely different. And then we had a horrific massacre of all life on Earth, almost all life on Earth. And we, oxygen-loving life, emerged. And so even Earth has been many planets. So there's no reason to think they would all be similar to us. So that's the first point. But part of the reason it's so important to try and find signs of life, extant or extinct, in the solar system is that if we find life in the solar system, not just in the clouds of Venus, but in places like the liquid subterranean oceans of the moons of Jupiter and Saturn, or the atmosphere of Titan, which is a planet with a thick, rich atmosphere and oceans of methane. If we find life or signs of life at any point in any of these places that are completely different from the Earth, then we will know that life is not just inevitable, but extremely common and in many different ways. And that will be a really big deal for our calculations and our hope of finding life beyond the solar system. But so far, it's true, we only have the Earth. But even the Earth has many data points.
Okay, yeah, this will have to be the last question. We just lost a wonderful, Tom will be the last question, a wonderful colleague of Clara's, Dr. E.O. Wilson passed away recently, and I had the good fortune of discussing this very subject with him several years ago. What a mind-blowing experience that was. So last question coming from Tom.
Where's the $9 billion come from, and in whose backyard is the telescope?
So the budget was a great source of controversy. The original budget, which was set in, I think, 1997 for a launch in 2007, was only $500 million. And then the budget grew as the mission grew and delays happened, and the longer you take, the longer you have to pay scientists and engineers. And so it really ballooned. And so the money is partially provided by international agencies like the European Space Agency, but it is primarily provided by NASA through the government. And I know it seems like a lot, but it is the teeniest fraction of spending compared to other big spendings like the military spending on a yearly basis. And the NASA programs tend to spend money, but they return a lot of money. The sheer number of patents and technological drives that happen through NASA programs have more than compensated for the cost of those programs in the past, I mean. And so this is not dissimilar. We really had to push the extremes of human engineering to create this telescope, and that will be used in many other places. The telescope is in space, so it will not bother anyone. It is in what we call the second Earth-Sun Lagrange point, or just L2 for short. And that is a really incredible place in the solar system, which is this invisible point in the solar system where the gravity between Earth and the sun balance out. And so it's extremely stable and a very popular place to try and put instruments on so that it can stay on a very stable orbit throughout the entirety of its life. And so that's where it is. Well, it hasn't arrived yet, but it should in about a month and a half.